Hello, my name is Jason Fernandez. Welcome to my heat transfer video assignment. Let's get started. So here's our problem. We have water flowing through a pipe. The inlet and outlet temperatures are 90 and 70 degrees, so heat is leaving the fluid. Outside the pipe, there's air blowing across at 10 degrees, and it's blowing at 40 meters per second. We get to neglect the thickness of the pipe. Nice. So in additional information, the surface temperature will be assumed to be around 60 degrees. We'll only use this for calculating our external convection factor. And then here are three questions. Calculate the surface temperature at the inlet and outlet of the pipe, calculate the total rate of heat transfer, and calculate the length of the pipe. So we'll go through the question again line by line, picking out some details. So we have hot water flowing at a velocity of 20 centimeters per second through a 2 centimeter diameter pipe. So here's our schematic. The inlet and outlet temperatures of the water are 90 and 70 degrees. On the outside of the pipe, there's an air temperature of 10 degrees being blown at 40 meters per second. And again, we can neglect the thickness of the pipe. So our assumptions, steady state, neglect radiation, smooth pipe, inside and out. There's no heat loss or heat generation. And again, we can neglect the thickness of the pipe. And this is also a one-dimensional heat transfer problem. So our approach to this question is that we're going to construct a thermal circuit. In this situation, we have a high temperature fluid and heat is leaving the fluid to the surroundings. So our direction of heat transfer is away from the pipe. And so our thermal circuit looks something like this. We have two sets of resistances, one for internal convection and one for the external convection, right? So heat leaving from the fluid to the surface and then from the surface to the surroundings. And so, we know the temperature at two locations, the fluid and the outside temperature. We're interested in finding the surface temperature. Between these two locations, we have two sets of resistances. And, both of these we can calculate. Once we calculate it, it'll be kind of easier to move forward. In this example, we don't know the area of the pipe. So I'm going to do things in terms of heat transfer flux. So I'm going to neglect this area. And that's the general idea for approaching this problem. So I'm going to start with calculating this external resistance because it's a bit simpler. So reminder that, we can assume a surface temperature to be 60 degrees. And again, the air temperature is at about 10 degrees Celsius. So we're going to use the film temperature. That's just the average of the two. So 35 degrees. I'm going to get the air properties at this 35 degrees. Here they are. For calculating external flow, well, first thing we want to do is calculate the Reynolds number. So that's pretty simple. Just plug in the numbers. We get 48,000 as our Reynolds number. From here, we can go to our correlation formulas and calculate the Nusselt number. And so this equation only depends on the Prandtl number and the Reynolds number. Again, we can just plug in the values and we get a Nusselt number of 135. And then lastly, we can convert, we have a relationship between the Nusselt number and our fluid property. So we can calculate our H value. And so we get 178.2 as our external convection factor. I'm going to also assume that this convection remains constant throughout the question. Now we've calculated our external convection resistance. Now we're going to focus on the internal resistance. To do this, it's a bit tricky because, first we calculate the Reynolds number, then we calculate the Nusselt number, then we can calculate H. The only problem is that the Reynolds number depends on density and viscosity, and both these properties depend on temperature. And like we said earlier on in the question, the inlet temperature and the outlet temperature of the fluid are different. So we're going to have two different Reynolds numbers. We're going to have two different resistances at the inlet and outlet. So we have to calculate two internal resistances, one at the inlet and one at the outlet. So focusing on the inlet first, we're going to get our properties at the inlet temperature, so at 90 degrees. Next, we're going to calculate the Reynolds number. I get it to be 12,000, so this makes it turbulent. And so I'm going to make this assumption that the entrance region for this system is very small and it can be neglected. Doing the calculations, it's only about 20 centimeters long, and I'm going to assume this is very, very small relative to the length of the pipe. So after we find our Reynolds number, we can find our Nusselt number. Here's the equation for it. Plugging in the values again, we get 52.2 as the Nusselt number, and then again, we can relate that to our properties and calculate the convection factor. And so for the inlet, I get the convection factor to be 1,771. So for calculating our H value at the exit, it's the exact same process. We follow the same procedure. This time I'm going to get my properties at the exit temperature, which was 70 degrees. And I'm going to follow the same procedure. First, calculate the Reynolds number. One thing to note is that we get a Reynolds number of 9,000. So it's still turbulent. However, to use this relationship to get the Nusselt number, our Reynolds number is supposed to be greater than 10,000. So I'm going to make an exception and still use it here. But it's just something to note down that this isn't going to be as accurate as it should be. So again, calculate the Nusselt number. Then from there, we can calculate the H value. And so I get it to be 1,558. That's great. So now we have our external convection factor and our internal convection factors. And so, right away, we can calculate our thermal resistances. And again, we're trying to calculate Q. And once we calculate Q, we can figure out our surface temperatures. So first I'm going to start by calculating the inlet surface temperature. And for that, I'm going to look at the values we found at the inlet. So that means our internal convection resistance is going to be the one we found at the inlet. For our external convection, well, it's going to be the same at the inlet and outlet. And so our delta T is going to be between the fluid at the inlet and the surrounding temperature at the inlet. So here's our thermal circuit. And again, so our delta T here is going to be from the fluid to T infinity. So we're skipping the surface temperature for now. So, plugging the values, we get a heat transfer rate of about 12,000. It's negative because heat is leaving the system. And so this same Q value, this heat transfer rate, is going to be the same over just one resistance. So just looking at the fluid itself, convection at the fluid, so between the fluid and the surface, it's the same Q value and it's the same R value, the resistance. So we can calculate our surface temperature, and I get it to be about 82.6 degrees. And at the outlet, it's the exact same procedure, except this time we're going to use the values we found at the exit. So yeah, just plug in the values again and get 63 degrees. So part A of the question was to calculate the surface temperature at the inlet and outlet, and here are the values we got. Intuitively, this makes sense because both these values are between the fluid temperature and the surrounding air temperature, which is what we'd expect for a surface temperature. So the inlet temperature was the fluid inlet temperature was about 90 degrees, and now it's 82 degrees at the surface. The fluid exit temperature was about 70 degrees, and now it's 63 degrees. So I think we're on track. And so earlier we made an assumption that the surface temperature was going to be about 60 degrees all throughout. Is this valid? I would say it was a good assumption. Our average surface temperature is about 73 degrees, and 60 is pretty close to that. I'm not satisfied with this, so I would do it again. So I'd do another iteration, assuming our surface temperature to be at 73 degrees. We would calculate our film temperature from there, find our air properties from there, and then go through the whole same procedure again. Recalculate the Reynolds number, then the Nusselt number, then the H factor, set up our thermal circuit with our new resistance, and then see what we get for our surface temperatures. So part B of the question is to calculate the total rate of heat transfer. This is pretty easy. We can use this energy balance equation, just focusing on this left side, MCP delta T, and our delta T is between the fluid at the inlet and the fluid at the outlet. So, pretty straightforward. We don't know our M dot, but we can figure that out from rho VA. And A here is our cross-sectional area of the fluid. I'm going to find our properties at our bulk temperature. So the fluid entered at 90 and exited at 70. So the average of that is 80. Finding our properties at 80 degrees, plugging in our values, we get a heat transfer rate of 51,000. This is leaving the system. So part C of the question is to calculate the length of the pipe. We can use our energy balance equation again, this time focusing on the other side. AH delta T at logarithmic mean. So our H value is going to be the average of the two convection factors we found earlier. So I get that to be 1,665. Our delta T logarithmic mean, we have to calculate that. This equation only depends on two values, delta TE and delta TI. And in both those cases, it's just the temperature between the fluid and the surface at the exit, and then the temperature of the fluid and the surface at the inlet. And so, those are pretty easy to calculate. We had at our exit, we had a temperature of 70 degrees and a surface temperature of 63. At our inlet, we had a fluid temperature of 90, surface temperature of 82. So, we can plug in these values in. We get a delta T logarithmic mean of 6.78. And so now we have everything to plug into this equation. We have we have H, we have delta T logarithmic mean, and we have Q. We're going to solve for A. One thing to note is that this A value is the surface area where the fluid touches the surface of the pipe. Now that's going to be pi dl. That's going to be pi times the diameter times the length. So that's what I wrote here, pi dl. And so, solving for L, we get 7.2 meters. And so earlier we made an assumption that we couldn't neglect the entrance region. We said it was about 20 centimeters. And so that assumption was safe to make because that's fairly small compared to 7 meters. So we have a bonus question here too. It says, how would the solution change if we included the thermal resistance of the pipe if it had a thickness of about 0.5 centimeter? And if that were the case, it wouldn't be too challenging. We would just have to add an extra resistance to our thermal circuit. It would be the conduction. It's not too challenging to figure out. We can calculate that simply by, we have our radius and we have our thermal properties of it. We can calculate that, add that in. And it would be the same procedure again, where we calculate the overall heat transfer rate of the system, of our circuit, and then we can use that to figure out, delta T's between two different points. In terms of how would it affect our surface temperature? Well, because if we have an extra thermal resistance, decrease our Q value, which means our delta T between the fluid and the surface would be smaller. It wouldn't be as hot. Also, if the radius decreased to 1.5, well, then we'd have to recalculate all our values again. Our Reynolds number would decrease, our Nusselt number would decrease, our H would decrease, so our thermal resistance would increase. And so, so now our thermal resistance of convection at the fluid would increase, and our thermal resistance because of the pipe would be newly added. So overall, Q would decrease and surface temperature would decrease. So what about our rate of heat transfer? Well, if the diameter of the fluid stayed the same, if it was still 2 centimeters, then there would be no change here. We'd still have the same delta T of the fluid, have the same thermal properties. So that would be the same. But because in this example, they say that our inner diameter changes, well, that means our mass flow rate, our cross-sectional area would decrease, so mass flow rate would decrease, so our overall Q would decrease. In regards to the length of the pipe, well, if our heat transfer is decreasing, then the length of the pipe would have to increase to make up for the same, in order to allow for the same change in temperature. That's all I have for you, and thank you for your time.